All right, I finished my general announcements. Not really a whole lot to say. 7.1 textbook work is dead today. The 7.1 Canvas quiz can be retaken until Sunday midnight, and Monday morning I'll be releasing the 7.2 Canvas quiz. Okay, go ahead and turn to 7.27. As I said, today is going to be a I do one, you do one type of day, and we're hoping to get through 7.210. Okay, so the point of what we've been discussing for quite a while now with the large counts condition is that if the large counts condition is met, we can use distribution to calculate probabilities involving the proportion of success given some random sample size n. So to be able to do the stuff that we're doing right now in section 7.2, you need two pieces of information. What proportion of success do you expect, and what is the sample size that you're taking? If you have those two pieces of information, then you can check necessary conditions and apply the mathematics we're learning. In the example we're about to look at, we're going to look at very, very large sample sizes. We're going to look at a sample size of 1,500 people where the presumed success rate is 35%. I realize I haven't read the question yet, okay? But if you take 35% of 1,500, what that means is you would expect around 525 successes, okay? So this is a picture that represents that, where if I'm able to click on the highest dot, which I will try, I think it's that one. Oh, 524. I was one off. There we go, 525. So if you have a sample size of 1,500 people and the expected success rate is 35%, well, then you would expect to get 525 successes, and that is the most likely outcome. However, the chances of landing on that exact marker is only 2%. And that's because there's so many other options. Okay, you can land at 526, 523, 527, 522. There's like a gajillion other options out there. Okay, so while that is the most likely outcome, the probability of getting that exact outcome is still very, very small. All right, so I'll come back to this in a moment, but let's read the problem. So a polling organization asks us an SRS, or simple random sample, of 1,500 first-year college students how far away their home is from the college campus. They are assuming 35% of all first-year college students attend college within 50 miles of their home. Okay, I know that that applies to me because I'm a graduate of Montgomery County Public Schools. I actually graduated from Watkins Mill, and then I went to University of Maryland College Park. So the college I went to was within 50 miles of where I grew up. Okay, so I would be part of this 35%. Calculate the mean and standard deviation of the sampling distribution of p hat based on their assumed p equals 35%. So the whole idea is you are told that you should expect 35%. So if every single one of you right now goes out and gets your own sample of 1,500 students, and you all report back to me what proportion of kids said that they live within 50 miles of this college, I'm expecting you all to tell me something around 35%. So the mean of the sampling distribution, 35%. Okay. However, how close to 35% should I expect you to be? Like if you come back and you're like, well, I had 34%. Is that really surprising? Is 33% surprising? Is 32% surprising? Like how far from 35% do you need to land that I think it's unusual? And that's what this formula is for. This formula literally says, what is a typical amount of variation from 35% in samples of 1,500? That's what this is meant for. Okay. So to interpret that value, and this is where I will pause and give you a chance to write, if I'm going to interpret that value, I have to refer to three different numbers. All three of these values need to be part of my interpretation of that number. Okay, because that number, that 1.23%, came from the presumed proportion of 35% and the sample size of 1,500. Okay, so in simple random samples of 1,500 first-year college students, I expect the proportion whose home is within 50 miles of the college to typically vary by about 1.23% from 35%. Okay, and this is where I'll pause because I know that's a bit to write. So if you were, let's again take an annoying trip back to chapter 6 for a moment. If you were going to build a probability distribution for this scenario, something that I personally would never, ever, ever, ever want to do unless I was building in an Excel spreadsheet that could do it for me, I would have to have a table that starts at the number 0 and goes all the way up to the number 1,500. And then I would have to find the probability of that many students in that sample of 1,500 saying, yes, I live within 50 miles of my home, or I go to college within 15 miles of my home. Okay, so I'd have to find 1,501 probabilities and build that chart. And if I took all those probabilities and put it into some kind of display, this is what that display would look like, where it would peak around 525. And the further you get from 525, which is 35% of 1,500, the rarer and rarer and rarer the probability becomes. And by the time you get even just looks like about 75 away from 525, the probabilities essentially drop to zero. Like if you should expect 35% at 525, well, then the probability of only observing 450 is basically zero, and anything less than that is basically zero. It shouldn't happen, okay? Now, if we want to find, we want to sort of say, well, these probabilities do a pretty good job of following a normal curve. So we want to represent those probabilities not by finding every single one of those individual probabilities, but we want to represent those probabilities using a curve that follows them, okay? Now, we have to justify why we're allowed to do that. That's this next part. Justify that the sampling distribution of p hat is basically normal, okay? And to do that with a sample, like I will admit, on the AP exam, if you ever encounter a situation with a sample size this large, very, very often in the grading rubric, when they say check the conditions, the grading rubric will say, if they didn't bother to check the large counts condition, just ignore it because it's so obviously large enough. It's 1,500. Okay, but I'm going to teach you to always check the conditions. Never can know if they're going to want it to be a part of the work or not. So I would show the sample size times the success rate is at least 10. I would show the sample size times the complement of the success rate is also at least 10. And because both of those values are at least 10, yes, we are justified in using a normal curve to represent the underlying population, underlying probability distribution. All right. Part D says, assuming their value, so let's assume this is a good picture of what should happen when they go out and take a sample of 1,500. Calculate the probability an SRS of 1,500 first-year college students will contain at least 37.5% of them live within 50 miles of their home. Okay, so we need to find on this normal curve, which is centered on 35%, where is 37%? Now, 37.5%. By the way, 37.5% of 1,500 is 562.5. So on this curve, 562.5 is somewhere out here on the left. So that's what we're trying to find. Okay, if they're telling the truth that it is 35%, then how often in a sample of 1,500 will you observe 37.5% or more? That's what we're trying to figure out. Okay, so this is the question we ask ourselves. How unusual would a sample result of 37.5% be when we assumed the result would be 35%? So that's how much of a difference we got. And a typical amount of variation is 1.23%. That's the number on. Turns out that kind of result would be slightly more than 2 standard deviations above expected, which by our standards would make it unusual. The probability for which, because that's what you were asked to find, calculate the probability, is about 2%. So if 35% truly is accurate, then when this group of people that are collecting data on college students gets a sample of 1,500, they really shouldn't see 37.5%. Okay, that typically shouldn't happen if the real answer is 35. And that's going to relate to the question on this particular page. Last question on this page says, the polling organization is wondering if a higher proportion of students are staying closer to home when they go to college. If the results of their SRS of 1,500 first-year college students finds 37.5% of them live within 50 miles of their home, what conclusion should the polling organization reach regarding their assumed value of 35%? Hint, use your answer to part D. So let's be clear. The polling organization goes out, they get a sample of 1,500, they observe 37.5. There are two possible explanations for that. One is the true answer is 35. They just happen to get a really weird sample. Okay, that happens. Even if they're taking a fair sample, you can happen to get weird results. But we as statisticians would argue that's probably not the best explanation because that should only happen 2% of the time. Like, yes, it could have happened just because, but it only happens just because 2% of the time. So perhaps the better explanation is that the assumed value of 35% actually isn't accurate, and their theory that maybe a higher proportion of students are in fact staying closer to home is the actual truth. And that would be the way I lean. And I would lean that way based on the fact that the probability is less than 5%. Okay, so that 2.11% is less than 5%, it seems more students are staying closer to home. Okay, and then I just talk about what that 2.11% means. That's the in green. Okay, that's what's written in green. If 35% was accurate, then observing a sample proportion of 37.5% purely by chance is very rare. It shouldn't happen by our standards of less than 5%. So I gave students about 10 minutes to work ahead of me on 7.28. About halfway through, I revealed my answer key to A and B. It's up to you all to speak up if you have questions on any of these. Okay, at the bottom of the page, you're asked to find the probability of at least 8%. So this is sort of an array of what you would actually expect. If you have, actually, now I'm thinking about it, I think I put it at 8%. Shouldn't it be at 6%? Yes. There we go. That's where it should have been. All right. So this is a model that shows, okay, if you go take a sample of 200, okay, and you expect 6% to be bruised or blemished or whatever it is, well, then the most likely outcome is going to be 12. Okay. Now, you can find any one of these probabilities. For example, if I asked you to explain to me, there's a number that says 16, 0.05. And if I asked you, explain to me what that 5.4% means. There's a lot that goes into the existence of that probability. Okay, sample size of 200, assumption of a 6% rate, and you want to know what's the probability you get exactly 16. Now, if this was a question from chapter 6, that is a question that is large enough that it would be annoying to have to do without a calculator command. Okay, you would literally have to say, all right, I have 200 potatoes and I want to choose 16 of them. There's a heck of a lot of ways to do that. And every single one of those ways involves 16 potatoes that are bruised or blemished or whatever it is. And the other 94% that complement to that is the other 184 potatoes. This is how you'd have to calculate that 5.4% number if you were doing it, quote unquote, by hand. Okay. You would never be asked a question like this because the numbers involved are so large that you would argue that one could absolutely argue you need a graphing calculator to be able to do this. Okay. So, the other way, of course, is using the binomial PDF command. I've got a sample size of 200. My success rate is 6%. I want exactly 16 of them. Okay, that's another way of getting the same thing done. But again, because the numbers are so cumbersome and they would literally require the use of more advanced technology, what we do is we say, well, there's a curve out there that sort of maps basically what's happening. You'll notice, by the way, it doesn't do a perfect job. You'll notice the curve actually misses several of those dots. I would argue that part of the reason that's probably happening is because we barely met the requirement of at least 10. We're at 12. So it's like, yes, the probabilities are normal enough, but it's a normal model approximation. It's called that for a reason. All right, so I'll finish belaboring the point. How unusual would be 8% when you expected 6%, and this 1.68% is how far you typically vary from 6% in samples of 200. Turns out that it would only be about 1 and a fraction of a standard deviation above expected. And so that's going to happen about 11% of the time. This should guide your answer to part B. So if the producer finds convincing evidence more than 6% of the potatoes in the shipment have blemishes, the truck's going to be sent away. If they take a sample of 200 and they find 8%, is that a reason to say, okay, this farm is lying to us? Way too many of these potatoes are contaminated or bruised or whatever it is. We need to send this truck back. And the answer to that question is no. You don't have evidence to send the truck back. You are aiming at 6%. The truck produced 8%. Yes, that's more than 6%. But even if the farm is actually producing potatoes with this defect rate of 6%, you're going to get trucks that have 8% or more 11% of the time. So that is a typical amount of fluctuation around 6%. It's not something that fluctuated high enough above 6% to convince us we're above 6%. Okay? So if you send this truck back, you're basically punishing the entire farm for something that might have happened by chance. Okay? Questions? All right, go ahead and turn the page. Okay, this is going to be another round of I do one, you do one. These problems don't have the conditions for you to write out, so they're a bit faster. Okay, I also don't ask you to interpret the standard deviation. So again, these problems are a bit faster. So police census data shows 75% of cars on the highway exceed the national highway repeated samples of 50 to claim. So already there's a claim, 75% of cars on the highway are speeding. The National Highway Safety Administration says we're going to take random samples of 50. They're expecting to get about 75% of the car's speed. By the way, 75% of 50 is 37.5. So they're going out getting samples of 50. They're expecting around 37, 38 people are speeding at the time they take their random sample. Okay. Given P is the proportion of cars exceeding the speed limit, label the normal curve below to model the sampling distribution for n equals 50. So all of you imagine each of you goes out and gets your own sample of 50. And then you report back to me what proportion of your 50 random cars were speeding. I am expecting you to report back to me 75%. But obviously, if you don't come back with exactly 75%, that's not a problem. That's just random chance. So we're going to build the normal curve. Okay. And it says, then find the probability more than 80% of the next 50 cars, that would be 40 cars, by the way, will be speeding. Assume all necessary conditions are satisfied. This statement, if you ever see that on the AP exam, is a beautiful thing because it can, depending on the problem, save you a lot of time and effort. This is what you need to write out if you were told to check the necessary conditions. Do you actually have representative data? Okay, we were told these are random samples. Okay, I'm actually realizing now I need to retype that. Okay, do you have independence? Well, I can't necessarily assume every car is independent of the others because, of course, they're following each other necessarily, but 50 is definitely less than 10% of all cars on the highway, so I'm fine with that. Do you have enough data? Well, I expect 37.5 speeders. I expect 12.5 non-speeders. Both of those numbers are above 10. This is all the stuff you'd have to write out if you weren't told the conditions are satisfied. Again, I'll have to reword this because this should have just said random, oh, they didn't actually say random. Okay, I assume the next 50 drivers are representative. Okay, they didn't say they were random. They should have been. So I'll assume the 50 cars are random. I'll type it out that way. In any case, so we do this mathematics to find how much will you typically fluctuate from 75. That builds the following model. Now, I put that in green for a reason because I'm going to repeat that exact same calculation in my work to decide how unusual 80% would be. Okay? So that z-score work, that z-score calculation is literally saying or asking the question, how unusual would observing 80% be when you thought it would be 75%? And that crazy thing in the denominator describes typical fluctuations from 75% in samples of 50. And you end up with a z-score. I mean, I can see it in the picture. 80% isn't even a full standard deviation above expected. So without even doing the math, I'm already expecting something that's less than 1. I end up with a z-score of 0.817. The area above that marker is about 20%. And that's the answer to the question. So everything else I wrote here, by the way, is just a verbal explanation of what that number means in context. So if I asked you, explain your answer in context, what I just circled in green, you would want to say, assuming 70 speed or highway driver speed, I would expect more speeders in samples of 50 about 20.7% of the time. Now, I know that there is a lot written on the screen, so please just take a moment and actually in blue, okay? There's a lot on the screen there, but it's show me some work, give me the z-score, give me your answer. And the problem did say label the normal curve, so that's why that part's also in blue. Okay? Questions? Now, because I don't like the way that's phrased. It feels like it's disconnected from the wording of the question. Clock is running. I'm just using the screen. Oh, I keep saying interstate. That's better. All right. Real quick, just side comment in case anyone caught this. I retyped the way I phrased this randomization condition. Again, you didn't need to write it because you were told the conditions are satisfied, but I didn't realize that I've read this as they took random samples, not repeated samples. So I will assume random samples were used. okay, is what I should have said up top. In any case, getting to the problem that I asked you all to complete, let me hit my recording.